All right, let's dive into a really fascinating, kind of hidden chapter of scientific history. This is a story about a question so simple, so fundamental, that science actually banned it. And then we'll talk about the revolution that finally brought it back.
Yeah, I know. It sounds almost unbelievable, right? For the better part of 100 years, the one question we all ask from the time we can talk, why, was basically off limits in science. We're going to unpack exactly how that happened, and then look at how a few brilliant minds finally gave science the permission and the tools to start asking it again. Okay, so to get this, we've got to go back in time. Picture it, the early 1900s. The brand new field of statistics is just getting going, and it's making this huge promise to bring cold, hard, mathematical rigor to all these messy, complex problems. But, in that rush for pure objectivity, its pioneers, well, they made a decision that would change everything.
You had these really influential thinkers, guys like Carl Pearson, who basically said, look, real science should only describe what it can see. It should only talk about relationships, how two things move together. The why part, why one thing causes another, they saw that as, well, too philosophical. It was messy. You couldn't just pluck it out of a spreadsheet. So they decided to just leave it out.
And this idea, it really took hold. I mean, for decades, the entire field of statistics was operating in what you could almost call a causal dark age. That little phrase we all learn, correlation does not imply causation, it went from being a helpful warning to a hard, unbreakable rule. It became, you will not even speak of causation, period.
So look, this wasn't some kind of, evil conspiracy to hide the truth. It actually came from a pretty reasonable place. For one, philosophers had been arguing for ages that you can't literally see a cause. You can only see one thing happen and then another. But the real kicker, the math of the time was beautiful for describing correlations, but it had absolutely no language, no tools for causation. So the easiest path was just to forbid the question entirely. But this had huge, massive, real-world consequences. Think about this. Researchers could clearly see this powerful statistical link between smoking and lung cancer. The numbers were undeniable. But because they didn't have a formal language for cause and effect, they were totally hamstrung. They couldn't stand up and say, with the full backing of statistical science, smoking causes cancer. Entire fields, from medicine to economics, were basically flying blind. So this century of, let's call it causal silence, it was finally broken. And the person who did it, interestingly, wasn't a statistician. He was a computer scientist named Judea. And what he did was develop this totally revolutionary framework that would, at last, give science the power to ask why again. What Pearl proposed was this beautifully simple, but really profound model for how we understand the world. He called it the Ladder of Causation. And his big idea was that pretty much all intelligent thinking happens on one of three distinct levels, or rungs of this ladder. Okay, so the first rung, the bottom of the ladder, is association. You can think of it as just seeing. It's the world of observation, of spotting patterns. You see smoke, you often see fire. That's association. This is where mainstream statistics was stuck for 100 years. And get this, it's also where most of our super powerful AI today still lives. Now, the second rung is a huge step up. It's called intervention, or doing. This isn't just about passively observing anymore. This is about actively changing something to see what happens. So you're not just noticing that people who happen to take aspirin have fewer heart attacks. You're asking a totally different question. What happens if I make someone take aspirin? See the difference? This is the world of actual experiments. And then, at the very top of the ladder, you have counterfactuals. This is the realm of imagining. And honestly, this is where things get really deep. This is that uniquely human thing we do, where we reason about what-ifs and alternate realities. It's asking questions like, would that patient have survived if we had given them the drug? It's the source of everything from regret and blame to credit and responsibility. Okay, so we have this ladder, but how do you actually climb it? Well, this is Pearl's genius. He gave science a whole new toolkit. He created a formal mathematical language that could finally tell the difference between just seeing something and actually doing something. And at the absolute heart of this new language is this tiny but totally revolutionary idea. It's called the do operator. So in old school stats, you'd write something like P by X. That just means, what's the chance of seeing Y given that I've also seen X? But Pearl introduced
P by do X. This asks a completely different question. What's the chance of Y if I force X to happen? That little do might seem small, but it was the key that unlocked everything. It finally gave math a way to talk about cause.
And to actually use this new language, we need a tool. And that tool is the causal diagram. Now, these might look like simple little drawings with arrows, but don't be fooled. They're actually rigorous mathematical objects. What they do is force you to put your assumptions down on paper, to literally draw a map of how you think the world works. What causes what?
Okay, so this is all great in theory, but how does it actually help us in the real world? Well, for one, it gives us a powerful tool to stop our own data from fooling us. Let's take a look at a classic statistical paradox, where the numbers seem to lie.
This is so important for untangling things like Simpson's paradox. This is one of those really weird situations where a trend shows up in different groups, but when you combine them, the trend either vanishes or completely flips. So a new drug might look like it's doing nothing when you look at all patients, but when you separate them by, say, men and women, it's actually super effective for both groups. A causal diagram makes you spell out your assumptions, like maybe gender influences which treatment is chosen, and just like that, it tells you exactly which result to trust. All that confusing ambiguity, it just disappears. And you know, this whole causal revolution, it's not just some dusty old story for statistics textbooks. It's actually pointing directly at the next giant leap for artificial intelligence. Because, as Judea Pearl himself argues, pretty much all of our amazing super advanced AI today, for all its incredible power, is still stuck on that bottom rung of the ladder. It's a grandmaster at association, at finding tiny, subtle patterns in mountains of data. But it doesn't have any real understanding of the world. It can't tell you why it made the decision it did. So if we ever want to get to truly intelligent machines, what some people call artificial general intelligence, the path forward is clear. They have to climb that ladder. We need to build AI that doesn't just see patterns, but that can actually understand interventions, and maybe one day, even reason about counterfactuals, about what might have been.
So the big takeaway here is that the journey to real AI isn't just a matter of throwing more data at it or building faster computers. It's about something much more fundamental. It's about giving these machines a model of the world, an actual understanding of cause and effect, so they can finally start to reason instead of just, correlating.
Which really leaves us with this one final, kind of provocative thought, doesn't it? After an entire century of science telling itself that asking why was a taboo, we've come full circle to rediscover that it might just be the most important question we can ask. It's the engine that drives all human progress. And maybe, just maybe, it's the very definition of intelligence itself.